All right, welcome everyone. This is Joe Armstrong and the September Power Systems Virtual User Group webinar. So monthly webinars that I do. It's a beautiful fall day here in Rochester, Minnesota, the kind of day that you don't want to be inside doing webinars, but rather outside in the sunshine before the winter snows come. I only really have one announcement before we get going, one big announcement, and that is TechU. As you know, I'm a big proponent of TechU. I think it's the best conference that IBM puts on by far. Best conference that I've been into in my career is the TechU's. A lot of fun. Unfortunately, with COVID, it's a virtual TechU again this year, but still a lot of great sessions. Okay, there's over 600 sessions in English. I think there's a bunch of sessions in some different languages as well. Great sessions to go to. It's October 25th through the 28th. If you go to the Power Systems Virtual User Group wiki, there's a link to register on there. And since it's virtual, you don't have to travel. There's no expense for traveling, and it's way cheaper as well. So I think a lot of I guess benefits to it being virtual. Just don't get the fun of being there. A couple other things is that we announced Power10. That's what Bill and I were just talking about here a few minutes ago. We announced Power10. That's what we're going to talk about today. And I have Bill Starkey on here that's going to help us. The presentation materials are out on the wiki. There's two of them. There's one that Bill's going to go through, some charts, and then there's charts that I'm going to go through. Bill's going to cover the chip, the Power10 chip, and I'm going to go over the system, the E1080 system that was announced. We are going to do a replay link. I'll put that up as soon as I can after it's all converted, downloaded, and everything like that. So you can look for the replay link on the wiki when that's done, which reminds me that I should say that we are recording this. I don't know why you would be bothered by that, but if you are, you can certainly get off. Also, there's a Q&A panel and a chat panel on the WebEx event. We're going to look at the Q&A panel for questions. So if you have questions, please put them in the Q&A panel. Chat all you want in the chat panel. But if you have real questions for Bill or I or somebody else that might be helping us, put them in the Q&A panel. So with that, let's get going. First, I want to introduce Bill Starkey. Bill's a distinguished engineer. He's currently serving as the chief architect engineer for the IBM Power10 processor. And as you heard him say, he's also working on the Power11 processor now, which has actually been in the works for quite some time. So Bill's responsible for shaping the processor cache hierarchy, the symmetric multiprocessor interconnect, cache coherence, memory, I/O controllers, accelerators that he's going to talk about, and some of the logical system structure for the whole Power Systems thing. Bill's a master inventor, authoring over 300 patents, and he received his BS in computer science from Michigan Technological University. Go for them. So with that, Bill's going to start us out here. So he's already the presenter. I'm going to turn it over to Bill, and then when he's done talking about that, then we'll about the chip in specific, then we'll kind of move into the system stuff. So with that, go ahead, Bill.
All right, thank you, Joe, and thanks everybody out there for the opportunity to tell you. It's very exciting now that we've launched this thing. You know, it's like birthing your baby, and just, you know, kind of a really exciting time for myself and the rest of the development team. We've been working on this thing for 5 to 6 years now, so it's been a long time coming, and happy the day is here now. You know, this is the chip, so I'll just hold it up a little bit to the camera. That's you can see that's how big one of these chips is, about the size of a postage stamp. You basically take that chip and then you put it in one of these things. You know, this is the module, and on the back side of the module, you know, those are all the connections that connect the module down and onto the planar. On the front side, this is a lid, and there's a Power10 chip kind of nestled underneath there, with all these signals on the back feeding it. And kind of a cool new thing with Power10, you see these connectors on the top of the module. That is a brand new technology, and that's very instrumental in our E1080. The actual SMP cables that connect drawers together, instead of running through the planar, they end up connecting all the way into the module, and that's part of what gives us our great signaling capability to be able to run those cables at the bandwidths and speeds that they are. They're actually interfacing right up with the processor module for the first time ever, not having to go through the system planer. You know, you obviously in a 1080, you put 4 of these things down kind of side by side and put massive heat sinks on them, and they're kind of the center of that nice system chassis that you have. But just to give a feel, though, once again, that's all that stuff. But you know, I'm going to be talking about just what's on the chip itself. So with that, let me go ahead and start sharing here. One other thing while I'm going, you know, Joe mentioned the TechU. I'm very excited. I'm going to be doing a session at the TechU as well. So I'd be happy to have, you know, any of you join me. But one quick disclaimer is the content I'm going to share in that session is going to be very similar to what I'm talking about here. So if you hear this and you kind of, you know, want to hear it again, maybe go into more detail, or you want an opportunity, I think it should be a little more interactive there, because we won't have like 600 people. It should hopefully be kind of a smaller, more intimate setting where we can, you know, maybe do a little verbal Q&A if that's possible. I'm not sure what the numbers will be, but typically those sessions, you know, don't run with 600 people. I have no idea what a virtual TechU is going to look like, but just an FYI, I'll be hitting, you know, very similar content. So maybe that means you won't want to hear it a second time, or maybe that means you will want to join in. So this is actually a photo on this title screen. This is that chip that was so small, kind of, you know, enlarged up to this size, and I'll go into those details. First of all, you know, just I want to remind everybody, you know, looking at the roadmap over about the last 10 years, you know, we've been doing the Power 7 and Power 7 Plus, then the Power 8 family, the Power 9 family, and with Power 10, you know, it is a family in terms of, you know, our Power VM based large core offering, and we actually developed a small core offering, but it's fundamentally one chip. Unlike you know, the Power 8 and Power 9, where we had a few different flavors of the chips going into the power systems, and then once again, you know, Power 11, we're deep in development, so you know, expect the usual 3 to 3.5 year kind of cycle. You know, that's roughly the kind of time frames we bring these things out on. So I know that's way off in the future for all of you folks, but it's kind of my day to day right now. But so today we're gonna talk about Power 10. And this is kind of that expanded photo. So if you would have looked really, really close when I held up the chip, you would have maybe seen some patterns on there that look like these regions that are defined. You know, it's built in a Samsung 7 nanometer technology. That means the feature sizes are 7 billionths of a meter, you know, in size, and that's how you pack 18 billion devices onto that tiny little piece of silicon that I was holding. It's only, you know, 600 square millimeters, which is once again roughly the size of a postage stamp. We have a very robust metal stack. You know, we've always believed in bringing really high bandwidth. So, you know, this is not just your standard Samsung technology. It's Samsung augmented with IBM secret sauce. Part of that's the metal stack. Part of that's we put in an enhanced device, which allows us to, you know, run it at higher speed, get our higher frequency. And I'll get into the next chart. We have, even though it's one chip, we have a few different ways of offering the chip in terms of one chip or two chips per module going into the sockets. As you can kind of see on the photo of the chip, there's 16 physical cores. But from an offering standpoint, we only use 15 of them. That's mainly so that, you know, we can have a 10 core, a 12 core, a 15 core offering. I'm sure Joe will probably be going into that in more detail, what the different offering flavors are. But we want to make sure we can have a you know, a high enough availability. And so we decided to put a manufacturing spare in here. You know, I think that's ending up being a really good plan. With just 15 out of the 16 cores, you're still getting, you know, an incredible performance lift compared to the prior generation. You know, roughly each core is roughly 1.3 times as strong. You know, that's mileage varies depending on your workload, but roughly 1.3 times as strong as a Power 9 core. And then, of course, you have more Power 9 cores. The largest Power 9 offerings were 12 core offerings. Due to a limitation on availability of 12 core, you know, a lot of times that ended up being 11 core or 10 core offerings. But you know, with Power 10, we're growing to up to 15 core. So stronger cores and more of them, gives you kind of a nice generational boost. You see there's a massive amount of cache on this thing, over 120 megabytes. Energy efficiency was a major focus. That's a big reason we're going to be able to put 2 of these chips in a socket in some of our configurations. And the enterprise thread optimizations, that's part of how we're getting, some of that 1.3x performance per core. AI is a major focus. I'll get into that in more detail. And yeah, I'll crawl through. It's going to be quite a bit technical, but I'll try to, kind of bridge things. And also feel free to, ask questions in the Q&A, and, we'll have either Joe or someone else will kind of chime in and can kind of ask me your real-time questions if you're asking anything. The open memory interface, this is a new feature for Power10. I'll hit that in the next few charts. But bringing extremely high signaling bandwidth between the processor and the buffer chip. And so it's not just for Power10, but this is going to be a multi-generational Power10, Power11, most likely Power12 going forward. We're really building this thing for long-term durability of memory interface and composability. Our signaling interfaces, where we do our SMP interconnect, accelerator attach, clustering, we basically took all of that and unified it. So there's a set of signaling interfaces around the corners of the chip that are very versatile and flexible and can be deployed in a lot of different ways. I'll touch on that. And then finally, the PCI ecosystem. We are among the first to bring PCI Gen 5 out. Now you may ask, well, there's not a whole lot of Gen 5 stuff out there yet, but we want to have, a durability here so that your investment in Power10, you'll be investing in basically the future. So as the I/O evolves and more Gen 5 content proliferates, you'll be able to use that with your Power10 server. So that's kind of a high-level overview and actually a visual of the chip itself. But as I said earlier, I was going to talk a little bit about the ways we can offer the chip. Now, I don't want to take away too much from Joe's discussion when he's going to talk about the system offering, but I'll just kind of build the bridge here so that you see on the top half of the chart, we have the chip and actually that module that I held up. That's a single chip module that I showed you, with those connectors on it. And that's used in our largest E1080 based system. And so you see a diagram of that system kind of built out of those modules, just a logical diagram, showing the 16 sockets that you get spread across the 4 drawers for a fully configured E1080 system. The focus there is on core strength. We're bringing, because it's a single chip module, we can devote all the energy and all the cooling to that one chip. From a capacity and bandwidth, we can devote all of the signaling that feeds in and out of that module can go to that one chip. And that gives us sort of that more flexible connectivity where we can attach up to 16 sockets. So Power10 is also in the future going to be available in a dual chip module. And that's going to be used to complete the system family. So we'll be building our smaller 2-socket, 4-socket offerings based on that dual chip module. And once again, the reason we can put 2 full Power10 chips into a single socket is really due to our energy efficiency improvements that our team built into this generation. Now, what that does really mean, though, is you are going to kind of have 2 general flavors of 2-socket and 4-socket offering. One of them will remain with a somewhat lower core count, more commensurate with what you're seeing in the single chip module, maybe in the up to 16-ish core range. And that's really focused on still doing what you did in the single chip module, where you can devote all the energy and all the bandwidth to making those cores as absolutely strong as possible. So, if that's the type of, platform that you're running right now, where core strength is a key focus, and you want to really leverage those improvements in core strength, going from Power 9 to Power 10, and you're in the 2 and 4 socket space, you'll want to be buying one of those, modest core count offerings that's kind of more commensurate with what you see in the E1080 core count offerings. Now, on the other hand, the new space this enables, by putting two Power10 chips into a single socket, we can put a massive, massive amount of cores into that socket. So if what you wanted was just more cores that are not really stronger than Power9 cores, because we basically have to reduce the clock speed some, to feed all of those cores the energy, that can be a powerful way to like more than double your core count per socket. However, with a reduced strength core that's more along the lines of what a Power9 core might have been. So really a broader range of offerings, kind of the traditional, give me more core performance, with some core count increase, or just give me tons and tons of cores and make them roughly as powerful as they were last time, but now I've kind of more than doubled down on my density. So those are kind of the two themes. And so if you're in the market for those 2 and 4 socket offerings, that's just something to be aware of and watch out for. Is make sure you know exactly what type of way you want to take your platform forward. Let me get into the signaling interfaces that I mentioned. The first one on the left here, the Power AXON interface, as I mentioned, that this extremely high bandwidth signaling, it's physically living on the corners of the chips. And that's basically used, and I'll get into the next chart, for our composability protocols. How do we put more chips together or more things with them? On the right, we have really built out of the same signaling technology, but with different latency optimized protocols. We have our new OMI memory interface. So in Power8 and Power9, you had our CDIM based memories. At least in Power8, it was in all systems, and in Power9 in the enterprise systems. And really, what you should think of OMI is it's kind of the evolution of the next version of that. And so one thing that's different, and I'm sure Joe will probably get into this, the DIMM form factor is going to be different. It's a more modular approach and a more disaggregated approach with better resiliency because of kind of where different components are located. But so that's basically chewing up, the east and west edges of the chip are all devoted to signaling the memory. And we're taking a massive increase in the raw chip signaling to the memory. And once again, that's kind of meant to be a multi-generational thing. So we're actually not even exploiting all of that signaling bandwidth in the initial Power10 offerings, but we're providing bandwidth that we're going to have generations of growth on, which is really going to be a good thing. As these, the memory, we kind of want that to be able to be available across multiple generations as well. Just like we did with the Power8 CDIMMs, making them available in the large Power9 enterprise systems. We're looking to get to kind of a modular memory technology where we can provide that even more robustly in the future. So just looking quickly at what do we do with these interfaces. Let's start out on the right here. The OMI memory. We have our main tier DRAM kind of shown in the middle, and that's, you should think of that as your usual memory that you're familiar with. We're just kind of giving a nice bandwidth uptick to that type of memory. Like I said, the DIMMs are coming in different form factors. It's also an agnostic memory, though, which means it doesn't know about the technology. So it can talk to DRAM, but somebody could make a different kind of memory. So for example, you could build some super high bandwidth memory if you were trying to deploy in some kind of an HPC bytes per flop oriented application that did not need a huge memory capacity. One could come up with a GDDR based thing, and that would be a way of really exploiting that huge amount of terabyte per second bandwidth coming out of there. Now, we do not have that type of offering available at this time. We're not selling HPC supercomputing type systems here. We're selling enterprise systems. So they're going to want the higher capacity that you get from that main tier DRAM, and that's what we're offering right now. There's also the potential for kind of a slower but more dense, higher capacity, potentially persistent storage class memory. So those are things that we're always evaluating as well. And we built this OMI memory interface so that you can have the chip, and then you can kind of decide later on what kind of memory you want to develop and attach to it. So those are kind of the themes of what's possible in the all-my memory space. Going to the left side of the chart, that power AXON signaling interface coming off the corners of the chip. Once again, that's another terabyte per second, you know, 1 trillion bytes of data per second capable of running over that. And how do we use that? Well, its main use, it can be used to build a large SMP interconnect. So, you know, the E1080 with those 16 sockets. How are we communicating? Well, we're running over this interface, you know, connecting those 16 sockets together. It's also possible to use that interface, configure it differently, and run to an open CAPI accelerator attach. You know, at this point in time, we don't have any planned offerings in that space for the existing Power10 systems, but that functionality is in the processor chip. And then finally, a really cool new thing we did with Power10, our integrated memory clustering also runs over that interface. So as opposed to just using them to, like we do on the bottom left, to build a big, you know, E1080 type 16 socket SMP, you can also use those interfaces to connect multiple computers together and basically share memory between those computers. So, you know, that's a technology that we have in the processor chip. You know, we've kind of talked about it a bit over the last year. It's a technology that, you know, there's a lot of software that has to go along with that, you know, a lot of other things. So, you know, there's nothing supported in that area in the initial offerings. But once again, that's an area where we're working on software development. We're working with, you know, various ISVs and other partners, you know, looking at, you know, what are the best ways to deploy that technology. So those are all the possibilities out of the chip. I kind of like to show this chart, and I already kind of focused here. You know, what are the very first things that we're coming out with? So which of the capabilities are we focused on immediately? Well, with the largest enterprise servers, you know, the thing you need on the left there is that SMP interconnect, using that to connect up to those 4 drawers or 16 sockets. And, you know, I got some words on the chart. We have, you know, up to 8 sockets in our first GA. There's a later GA in a few months where we'll go up to 4 drawers. Joe will go into that more. And then on the other side, you know, what memory do we want? Well, we want our fabulous, you know, high capacity, high bandwidth, high reliability DRAM based memory. So we have a DDR4 based memory offering that, you know, runs it up to 410 gigabytes per second peak bandwidth out the backside. And in terms of the DIMM offerings there, we have our lower capacity DIMMs available now, and then in a few months with our later GA, our ultra high capacity DIMMs. And once again, I believe, you know, Joe will probably go into more details there. But so of all these sort of chip signaling bandwidth connectivity capabilities, you know, these are the ones that we focus on first, because these are the ones that are most important for the large enterprise system that we have just, you know, begun offering within the last month here. Let me flip it over to what are we doing in the architecture in the processor core. And just want to go through a few highlights. One thing we did, and this is another example of a long-term investment, you know, RISC architectures in Power, you know, like Power or ARM, or, you know, in the old days, PA RISC or Spark. You know, these architectures typically operate on a 4-byte instruction word. But, you know, being around for, you know, 30-ish years now, we do see some value in expanding that instruction space. So one thing we did to kind of lay down for the future to give us, you know, many more decades of, you know, architecture that we can build on top of these, we've come up with a way to do what we call prefixing, which allows us to build 8-byte instructions, which you can imagine if you have 8 bytes to put all your opcodes and you know, operands and you know, maybe immediate data fields, things like that, immediate address fields. It's just a very robust encoding space, and it's going to allow us to do a lot of things in the future. And we've actually exploited it to do, you know, quite a number of new instructions already in Power10. In the next realm, just in general, new instructions and data types, we've got over 200 new instructions for AI. AI is a key focus as we see the industry in general maturing in this space. And we see, our traditional enterprise workflows, our traditional, database things, our traditional analytics. We see AI more and more will be infused into these flows. So it's very important, to be able to execute the AI flows right in line with where the data is in the transactions. So that is right in the processor core. I know with Power9, we had a large focus on using GPUs to accelerate. And by the way, GPUs are great for accelerating AI training. But when you actually want to put the AI to use, to actually do the inferencing, to do the operating on your real data, you really want the execution there to not be off somewhere on a GPU. You can't be doing a big database transaction and then worry about, running off to a GPU to go do the AI over on the GPU and then wait to get your answer back. You want to do the AI right in the processor core where you're executing the database instructions. Oh, hold on, yeah, sorry, that went forward by accident. There must be a timer on here or something. The next piece, advanced system features. There's a number for persistent storage. There's some debug. We're doing further exploitation of our gzip compression engine, and then also, there's some things for the system software to use around, the memory, which memory is hot, which memory is cold, and also something called copy paste, where we can basically send 128 bytes of information atomically. That works really well when you're working, with the memory clustering. If you want to send messages, it's a great way to atomically send messages. With all our energy efficiency comes additional energy management capabilities, and then finally a strong focus on security. Really working closely across the stack. It's great to be one company. We don't just build chips. We don't just build chips and systems. We actually build, our system software as well. So, working closely across the stack through the chip, the system, up through Power VM, we're able to do a lot with security. One of those things, which is primarily a hardware thing, is we fully encrypt your data in memory. And we're basically building that right into the read-write flows of the memory, so there's no performance overhead. It's just running right in line with the big data pipes going in and out of memory. We greatly expanded our crypto capability. There's 4 times as many crypto engines in the processor core. We also have better controls for some of the options for security mitigations, and we got some return-oriented programming attack mitigation, kind of going after a specific attack vector with our architecture. Now, diving a little deeper, now this is a real scary chart, and don't worry, I'm not going to go into the details of this, but this is a picture of basically half of a Power10 processor cores, basically the execution pipeline. And you just want to focus here really to talk about relative changes from Power9 to Power10. The areas shown in green, the boxes in green, all had improvements relative to Power9. The boxes in blue were all at least doubled compared to Power9. So there you see kind of a big focus on the execution width, the instruction table. That's how many instructions can we have swimming around at one time. The execution slices are the number we can simultaneously execute. And then also our prefetching, our ability to go and leverage that high memory bandwidth that we invested in. Those were all doubled. But then areas of real extreme focus, the red boxes are areas where we've quadrupled. And that's basically a matrix math accelerator. So I talked about the AI, and I'll get into a couple charts in this in a few moments. But the matrix math accelerator, a really major piece of focus to be able to get extreme improvements in AI inferencing. The translation look-aside buffer and L2 cache. So those are both ways of making sure we can put more data as close to the processor as possible through the L2. And with the translation look-aside buffer, that basically increases our reach so that we can simultaneously access a much broader range of memory with the 4x size increase on the translation look-aside buffer. So those are kind of the major themes. And that goes into, how did we get the added performance shown on the upper left? On the lower left, we're really also talking about the energy efficiency. And there we focused a lot on additional clock gating, where we basically turn clocks off to areas that aren't being used, improved branch prediction, so we have less wasted speculative traffic. And then the fusion units are basically autonomically grabbing groups of instructions and fusing them together. So take like two regular instructions and combine them into a jumbo instruction to really leverage the double size of those execution slices. So, that's not even a matter where you need to recompile to use that new prefix architecture. We basically have ways of automatically on the fly turning old 32-bit or 4-byte instructions into new 8-byte instructions. And so that's another area of not only getting performance, but reducing energy. Finally, the L1 cache structure went to a whole new architecture where instead of having to do a translation lookup operation on every single load, we basically pushed that to only needing to do that on an L1 cache miss. And so that saves quite a bit of power in the core, making the load instructions a lot less expensive from an energy standpoint. So I promised I wouldn't go too deep there. Maybe I actually went deeper than I should have, but wanted to give you kind of that high level overview, just comparing a Power 9 to a Power 10. What were the things that we invested in the execution pipelines of the core? I'll flip over now just to talk a little more about what we did for AI. And one of the things is, and it's shown on the top half of the chart here, it's great to put a bunch of fantastic AI capability into a processor core. And by the way, we're not the only people doing this. You see in the Intel world, the ARM world, you see people kind of architecting these lower precision data types and investing in more capability here. It's just kind of the wave of the future as the industry embraces more AI infused, not only into enterprise workflows, but just across the board. But one thing that I think we are very unique in is our ability to feed the AI. It's very important for a lot of these algorithms that you're not just operating out of like an L1 cache or an L2 cache. You're operating on a massive data set that doesn't fit in the cache. It maybe has to come all the way from main memory. And so we really invested in having high bandwidth from main memory all the way up through the L3 cache, through the L2, through the L1, to feed the SIMD execution units, and then even our matrix math accelerator units. So that's really a key distinction, getting to those high bandwidths. And then there on the bottom, I won't read the chart, but just as I said, investing in not just the traditional 64-bit and 32-bit floating point, but investing in lower precision, which is so critical for AI inferencing. So we have two flavors of 16-bit floating point, and then also lower precision integer operations, which are also very interesting and important for AI inferencing. 16-bit integer, 8-bit integer, and we're even going all the way down to 4-bit integer. And by reducing precision, that means you can do more operations simultaneously. So you can see your peak operations per cycle. As you get to lower precision math, you can do many, many more operations per cycle in the processor core. Let's take that just to the next level. You heard me mention this matrix math accelerator unit. So this is kind of this extra thing that's even beyond that vastly improved SIMD execution. And it's aimed at specific types of multiply accumulate operations, and these are really at the core of AI inferencing. This is what the inner loop is these low precision, massive amounts of parallel multiply adds. And so we built a unit to do just that, and basically quadruple the number of operations at equal precision we can do per core. And then of course, when you go to reduce precisions, you can have massive speed ups per core. So not only does that increase the throughput, it's also improving the latency pretty substantially, especially as you get to the lower precisions in terms of getting to your inferencing answer. And part of the way we do it, we actually physically locate it kind of in one region of the processor core where we accumulate the results. This was something we worked with IBM Research on quite a bit, to kind of devise what's the best way to build a low energy architecture for this, so that you can really get a lot of this inferencing done, without burning a lot of power. And this is another area where I think we're kind of differentiated. Like I said, there's a lot of people doing these sorts of operations, but the way we built the state accumulation right into the matrix math unit, so you're not slinging the data all around across the processor core, but you're kind of operating it, right where it wants to sit in the processor core once you brought it in. That's really helping with our architecture. So with that, I think that's kind of all the themes that I wanted to cover. So I didn't really hear any interruptions during the presentation for questions, but maybe I can take a pause now, and I can't really see the chat because I'm seeing this full screen here. But Joe, are there any interesting things in the chat or any questions that arose that we should hit here?
So Bill, first of all, we've got Douglas Gibbs on, and he's been answering some of the questions in the chat. So he jumped on and offered to do that, so that's been good. Let's see. Douglas, you kind of been looking through them. Do you want to chime in and ask any that you didn't?
Sure. A good question we got here from Helmut was, is the L3 cache region a private region exclusively used by the local P10 core, or can this cache region be used by other remote cores?
Okay, that's a great question. Yeah, let me go a little bit into that. So we're kind of looking at this picture right here. And if you see there's that dotted line called local 8 meg L3 region. And this is really the way we've been building our cache architecture every generation since Power7, where each core has its own local region. And that's so really all the stuff in that region, or all the stuff that core uses sort of first utilizes that region, and that's to get the absolute lowest latency it can to that 8 megabytes of data. But then once it falls outside of that region, then it basically migrates to the local 8 megabyte regions of the other cores. And so that's where you get to the 64 megabyte hemisphere, or even across to the other side of the chip, the remote hemisphere. And I did get this question because we sort of draw them. It looks like sort of two separate 64 meg hemispheres. I get the question, is there a big latency difference between those two? The answer is, and it always has been, when you're on a chip and you're using this architecture this way, as we've done since Power7, there's always a little bit of advantage to be a little nearer physically to the processor, to the local processor cache. So there are some slight variations. The difference with Power10, though, is that we've actually substantially improved the latency. It's about a factor of 3x better when you miss your local region and you go somewhere else. So you get about a 3x better latency to that local 64 meg hemisphere. And when you go to the other hemisphere, you're more at about a 2x latency improvement. So there is a little bit of a difference there, but like compared to where Power9, Power8, Power7 were, it's just substantially better across the board. So hopefully that helped answer the question. I guess the other thing too, and maybe some people have heard our System Z, they just released their processor, and there was kind of a lot of fanfare around the Hot Chips conference, just like we had with Power10 about a year ago. And they talked a bit about this cache architecture that they have that's very similar, where you kind of start out in a local cache, you migrate around. We actually worked together quite a bit on that across our development teams. But the one thing different that there might be a question in somebody's mind, they actually use their architecture to propagate their L3 movement across multiple chips. And that's one area where we in Power have always decided to stop. We kind of, you have your local region by your core, and then you expand out to fill the chip. But we've never built it to share across the chips. It's just never been the right trade-off in our architecture. That is a difference. If any of these questions are coming from somebody sort of studying what System Z is doing, that's one difference. They will migrate across chips because in their architecture, they've determined that to be of value for them. So hopefully that was a complete and comprehensive answer to the question. Any others?
Yeah, and actually
Sure.
the System Z thing did come up, Bill, so that was good that you talked about that.
Good.
There was a question about affinity.
Looking at
did you want to talk about that one, Douglas, or is there a different one?
Well, there was two questions on Affinity. Both by Mr. Gordon here, I believe. In the past, with slower buses, switch speeds, bandwidth, caches, etc., Affinity was a concern. It's always a concern, I think we could safely say. You can't eliminate Affinity issues, but is it getting to where this is not significant anymore? Are speeds
So,
of...
So yeah, as
You know,
far
it was
as
a big
Okay,
deal
go
in
ahead,
Power
Matt.
7, and then it's become less.
yeah, as far as Affinity, you know, historically, you know, I think maybe those of us who've been around long enough to, you know, remember Power 7, you know, we definitely had some challenges on Power 7 that we very aggressively addressed as we transitioned to Power 8. And a big structural component of addressing that was going from what we called a 3-hop topology to a 2-hop topology. So Power 8, Power 9, and Power 10 all have that same 2-hop topology. So we were kind of living on, you know, a lot of that, you know, I'll say massive level of innovation that went into Power 8. You know, with Power 9 and Power 10, we've brought more in, but we haven't changed structurally. There is a focus, though, you know, even on the way we lay out the chip. You know, you might notice if you look at a Power 9 chip, it's laid out differently from this Power 10 chip. Part of this focus was on optimizing the latencies. And so we do enjoy kind of a substantial reduction in latency to the memory in the remote drawer. So if you have a Power 9 and you've got a latency to, you know, a memory in your remote drawer, you're going to get about a 25% improvement on that latency going from Power 9 to Power 10 because of, you know, some of the just the topological chip layout as well as some protocol enhancements that we put in Power 10. So, you know, do NUMA effects ever completely go away? You know, no, but, you know, do they get better sometimes? Do they get worse? You know, I'd say they're going to get, you know, a bit better going from Power 9 to Power 10.
Okay. So there's been a couple of questions I saw pop up on split cores and SMT4. None of that is announced, and there's nothing like that announced for the coming system that I'm going to talk about here in a bit. So we don't have any announcement on that. Not really going to comment on that. Based on what Bill put up here in the chip, I suppose it's probably possible, but just have to wait and see what we do with that. Since we have dual core chips, I don't even know where they're going to go with that.
Yeah, as far as, and I think I mentioned it, we have a capability in the chip to do, you know, either, and by the way, it's two different versions of the chip. So there's like the large SMT8 core version that's, you know, even in Power 9 when we introduced this, you know, all of our Power VM based offerings, you know, probably the things that this audience is interested in primarily are built based on the large SMT8 core. There is capability, you know, in there to do the 4-core versions of the chips. You know, at this point in time, we don't have any announced products around the 4-core, and yeah, I think we should just probably leave it at that.
Okay. So we probably should get started on the next part of the session so that we can get through that. Just gonna.
Okay, well, in that case, I'm probably going to turn my camera off, but I will just once again say thank you to everybody, and you know, feel free to follow up with questions if any more questions arrive.
All right, thanks, Bill. All right. Sorry, guys, I just need to share here. Okay, so how's that? Bill, can you see? Okay.
Yep, that's looking good.
All right. So everyone, we're going to transition in about talking specifically about the Power10 chip, but you know the chip isn't do any good until we wrap it up into a system and put lots of other things around it, DIMMs, power supplies, you know, adapters, and then everything like that. And so IBM announced the first Power10 system on September 8th, the E1080. We're going to talk about that. So before I jump off of this slide, I just want to point out a couple of things. The little logo up here in the top right-hand corner, that's the official Power10 logo. And marketing took a break from hassling me and made 3 new logos for AIX, IBM I, and Linux. I guess I'll have to change the ones in Power Systems VUG logo at some point. But so new logos for you to be on here, okay? So let's talk about the E1080 now. First of all, I'm going to cover a little bit about the Power Systems life cycle, okay? So we announced, actually, the Power10 is not just announced, it's available now. So it would be move over into the in-market here. And then systems moved to end of marketing, the Power 8. Power 8 went end of marketing in 2019, meaning we don't sell Power 8 systems anymore. Still supported, so not a problem there. And then they get to an end of support. Power 6, Power 7, Power 7 Plus are all there. Power 7 went end of support in 2019. And 7 Plus systems all went end of support last year. Even though they're end of support, you can usually get some extended support. It's limited based on best availability of parts. We're not making parts anymore. If we run out of parts, we certainly can't support them. So the extended support has some caveats on it. All right, so end of support for Power 8 is not announced. Usually we announce it, you know, relatively close to what it's doing, maybe 12 months or so. So Power 8 is not announced. I took some of these older systems and I looked, you know, when are they announced, when are they go end of marketing, when do they go end of support, just to kind of try and get an idea. So totally not announced. Joe's best guess here. Power 8 probably going end of support sometime starting in 2023 maybe. Might get pushed out even to 2024, 2025. That's, again, just my guess, okay? Nothing announced by IBM. I threw this slide up here just to kind of give you an idea. I think everybody probably on this call is pretty familiar with the IBM Power Systems. This is the Power 9 family. So we're going to talk today, the E1080 is going to be the replacement for the E980, okay? Big system. We also have lots of other systems in the Power 9 family. Probably have those systems in the Power 10 family. Nothing is announced. I'm not showing any roadmaps. I'm not announcing anything. But all these systems that about like this are to come. Now, I'll say they're not this year. They're later. So they're a little ways off. So don't be expecting anything on this, you know, in the near future. But we're going to really cover this. That said, a lot of the stuff I'm going to talk about, stuff Bill talked about, all applies to these systems, right? So if you don't buy an E980, you don't have 880s or 980s or 870s or these big systems, and you live in this small, what we call the scale-out world, you know, you can still apply a lot of what we're saying. You know, the Power10 chip's going to be in here, right? And a lot of what we're talking about is going to be in these systems. So kind of try and apply that if you need to. But it's still exciting to hear about what we're doing here, okay? So let's talk about the Power10 system now. And this slide, I'm not going to spend a lot of time on it because we're going to cover all of these things in more detail. But it's a follow-on to the 980. It's a modular system. As Bill said, it's made up of 4 CECs, Central Electronics Complex. You can also call them nodes or drawers, all the same thing. And we'll talk about that. But pretty much everything on this chart we're going to talk about in more detail. So I'm going to kind of flip past this, and I really put it in here so that, you know, as you download these charts and you want something to show, like to your management or something, this is a good one-pager that kind of shows the offering. But I think this shows it really a little bit better in that, you know, we have the E1080 is made up of multiple CECs. The smallest one you can buy is a single CEC. Bill said the Power10 chip comes in a 10, 12, and 15 core. So if you take the smallest one, there's 4 sockets on it. It would be minimum of 40 cores in this CEC. And then there's a 2 CEC version, a 3, and a 4 CEC version. Now for this announcement, IBM only announced the 1 and 2 CEC versions. Okay, so that's what's available today. The 3 CEC and 4 CEC versions are coming out later this year. So I think maybe December for these. So they're coming, they're pretty close, you know, they're imminent. So, you know, if you're planning, you can still plan on these if that's what you're looking for. But until then, today, you can only buy a 1 CEC or a 2 CEC system. But if we look for it, since it's pretty darn close, up to a 4 CEC system, 16 sockets in them, 4 in each CEC, 64 terabytes of memory, so we've still got lots of memory there, lots of PCI adapter slots, and up to 240 cores if you use the 15-core option in each of these. So we're going to look at all of that in a little bit more detail. In fact, if we pop onto this next slide here, here's a picture of the front of one of the CECs of the node. You see the fans here, and actually if we take that front cover off, well, before we do, it's 19 inches wide, fits in a 19-inch rack. We kind of moved from the big racks, I think, from Power7. Then we went to standard 19-inch racks for our enterprise systems. It's really the same size as the E980s. The drawer is 5U. The CEC is 5U high, so up to 4 of those if you're planning on space. If we take this front cover off, we'll see that we have the fans sitting in the front, and then the power supplies in the front. Okay, 4 of them, 4 power supplies. Redundancy, I think it can run on 2 power supplies, so redundant power supplies in the front. Take a look inside. You'll see the front here. We have the fans, and then the voltage regulator modules providing the correct voltage to all the different parts inside the system here. Memory comes next. Here's their 64 DIMM slots in the system, and then 4 processor sockets. Right? What you see here is the big heat sinks on top of them, and then cables connecting all those to each other, and the PCI slots in the back here. A little thing about the processor chips. Again, there's 4 of them in the CEC. Each chip has 10, 12, or 15 cores on it that are usable. As Bill showed, there's actually 16 cores on the chip, but only up to 15 of them are ever usable. So if you use 15-core chips, 60 in every CEC, that's 240 for the largest E1080 server. And these are all running up to 8 threads, so 1,920 concurrently running threads in the system. This is going to do a lot of work. One thing is in the system, all the processor chips, so if it's 10, 12, or 15 cores, they have to be the same number of cores. So they're all 10 cores, all 12 cores, or all 15 cores, and not just in the CEC, but in the entire system. All the CECs have to be the same. So they're all the same number of cores in the system. And then on the bottom here, you can see the speed, the clock speed of each of the different offerings, the different cores. So the 12-core system, interestingly enough, is the fastest clock speed and gives the best performance. Now, note that this is actually, it shows the clock speed there, but it actually runs in a range. When we came out with Power9, we have the range, and depending on the workload, the clock speed can vary. So if all the cores are really busy, the system is running at 100%, your clock speed will drop. and it mostly drops because the voltage regulators can only give so much voltage to every single socket. And so they max out what the voltage regulators will provide to every chip. But if your system isn't running, 100%, then your voltage goes up to these maximums. All right. Bill also talked about the memory interface. Here's the DIMM sizes that we have, 64 slots per CEC. And I'm not really going to talk a lot about this because Bill really covered the whole open memory interface and the benefits of that. It's more of a serial versus a parallel interface. And again, in the 1080, the whole 1080, the enterprise systems in general are built for resiliency, at the best resiliency, absolutely positive. So, there's, like I said, redundant power supplies in there. There's redundant service processors in there, redundant DIMMs on the memory interfaces. So just redundancy everywhere, and it includes the memory as well. Up to 1.6 terabytes per second in our bandwidth. So we're moving a lot of data on these systems. A quick look at the rear view of the system then. You have the power supplies where they plug in, the FSP, so communications to the FSP back here, and 8, in every CEC, 8 PCIe Gen 5 adapter slots. They're all Gen 5 slots on the system. I think in some systems in previous versions we came out with a mix of generations. In this case, they're all Gen 5. They do take a blind swap cassette. Now, we're going to get into adapters pretty soon, and you can move adapters from Power 9 to Power 10. The same adapters will move. However, the blind swap cassettes cannot move from Power 9 to Power 10, and so you need a Power 10 blind swap cassette. And then that adapter actually goes in the cassette, and then the cassette slides in and out of the back of here. And then we have the SMP connections for connecting the multiple drawers together, and then 32 gigabytes per second for each cable. And in the middle here, in every CAC, 4 NVMe SSD drives. Really, in the systems like the E1080, mostly everybody will have external storage, some kind of flash or something that's attached via fiber channel. These NVMe drives are great, really, for booting if you're booting VIOS from them. All right. Typically not used for a lot of data, mostly because of the drive write per day limitations on those drives. All right. So with every system, E1080 system, there's one control unit, and that really manages all the CACs together. So you have to have one control unit. It also is 19 inches wide, but it's just 2U high, same depth. And again, this is really the same size as a Power 9 system. So if you look at the entire system from the back, this is what one would look like. 4 CACs all stacked on top of each other with a control unit that sits at the bottom, and all nicely cabled in this particular picture. So let's look a little bit about adapters. I mentioned adapters. As I said, most of the E980 adapters are available for the 1080 as well. There's a few minor updates to them. And Bill also said that, Gen 5, everything's Gen 5, but there's not really Gen 5 adapters out there. Okay, so vendors are making Gen 5 adapters, or busy working on them anyway. They will be supported in here in the future, and that's the great thing about the E1080. It's really built for not just today, but for the next 3, 4, 5 years out, when you can purchase, more Power Gen 4 and Gen 5 adapters to get better bandwidth. The same I/O drawer that was used in the E980 will come over and be used in the 1080 as well, and the E1080. And the PCIe adapter drawer, the same adapter drawer, can move over as well. It does take a newer E1080 adapter, but the drawer itself can come over. And Douglas, if there's anything in here that you want to chime in on, Doug Gibbs is on here, and he's our I/O offering manager, so he can certainly chime in here.
There's lots I could say. I haven't. Sorry, go ahead then. I'll catch up later.
Okay, well, yeah, let's, we're going to get to adapters. We're going to show some adapters, and then I'll tell you what, I'll pass it over to you then, Doug, as you can say a few things then, okay?
Sure.
All right, let's see. So there's a few E1080 minimum hardware requirements I just want to go over. One is, of course, you have to have a single node. All 4 sockets have to be populated in the node. We don't have any nodes that are just 1 or 2 sockets or 3 sockets. So there's at least 40 cores in a node, 48 if it's 12-core system, or 60 if it's a 15-core system. At least half of the DIMM slots have to be populated, so you have to have at least 32 DIMMs and a terabyte of memory in there. I'll tell you, for the best performance on these systems, you want to populate all the DIMM slots. So as you're looking at this, you're trying to decide what you want in your system. Give a lot of thought to your memory. Don't say, oh, I'm going to buy this now and I'm only going to populate some, and if we need to, we'll fill up more later, because actually most people don't fill up more later, and it's better, you'll get just better performance if you fill them all up right from the start. Now you can fill them up and maybe not activate all of it, and we have a lot of people that do that, but just give some thought to that. So there's, like I said, 8 PCI Gen 5 they're low profile slots in here. You do have to have a single 2U, the controller system that I showed. That has to be, it's a requirement for every system. It has to be 1 for every system. 1 control unit can't manage 2 systems. And they all come with all 4 power supplies in them. And you need 2 HMCs connected, and I'll talk more about that on the next chart. They can be either virtual or physical. And some of the minimum activations. So of all the cores you have in the system, 16 have to be active for static cores. That is only if you don't use pools. We'll talk a little bit about that in just a second. And 50% of the memory has to be active in the system. Okay. So now, if your system is a pooled system, if you have PEP 2.0 in here, it's the same as we had for Power9. You only need one base core and 256 gig of a memory for base activations. We talked about on a bug session in June, dynamic capacity, and I covered pool PEP 2.0 in that session. So if you don't understand pools or something like that, I'm not really going to go into it now. We did a whole session on that. You can go back and look at the replay of that. But just know that if you're in pools, you only need one core active. And then Power VM comes with every system, so you have to have Power VM, which probably would on the E1080 class systems anyway. So I mentioned HMCs. There's a requirement of 2 HMCs for the system. There's options. You can do 2 hardware appliances. You can do a hardware appliance with also the virtual HMC, which you get the code and you load it on your own hardware. Or you can do 2 virtual HMCs. Now, the virtual HMC and the appliance have the same functionality, so you're not giving up functionality one way or the other. The only HMCs that work with the E1080 are the 7063 CR1 and CR2 appliances and the virtual HMC, of course, but only these appliances work. These are both power-based appliances. The older HMCs that were Intel-based appliances, the CR 8, 9, 7, all those old ones, do not work with the E1080, right? And so with the E1080, you have to put the HMC release 10.1 on there. Another thing is with 10.1, you cannot manage a Power 7, right? So these systems will manage Power 7, but once you put on 10.1, you can't manage Power 7. So what that means is if you're managing your Power 10, you're not managing your Power 7 with that same HMC, okay? So when you go to purchase your Power 10 system, look at your HMCs, plan for this and what you need. Get rid of your Power 7 anyway, all right? The HMCs have to be connected to the control node, both of them, and there's 2 service processors. In order to do firmware updates, it's a requirement that each HMC is connected to both service processors. And that's really just, again, it's a redundancy to make sure everything's going up and going right along the way. So now we're going to get into some of the adapter stuff. And I don't really have a lot to say. And in fact, this particular chart just shows what adapters are no longer orderable. They're not marketed by IBM, but if they're on your 980, if you have these adapters, you can move them to the 1080. All right, they're supported on the E1080. This next chart is a bit of an eye chart, and this is all the adapters that are orderable for the E1080. Now, I put this chart up here. You can look at it and see these, but really, you know, the adapters change through the life of the system, and fairly frequently, I think sometimes we get new adapters that come up, other older adapters drop off. So really, when you go to order your system, you really want to look at what's available and order from that. At this point, Doug, do you want to say anything else on here?
I was going to say, if there's enough, I know there's been numerous questions on the I/O. If we want to, not next week, but maybe in 2 weeks, I can do a half-hour session or 45-minute session on all the I/O. And I've got cleaner charts that break it all down into the different parts of I/O areas, and we can expand upon it at that point if you want.
Actually, that'd be great. So if you want to see more in-depth discussion on the I/O, in the survey that comes out when the webinar is over, please put in something in there and say, hey, we want to see some I/O stuff, and then I'll line something up on that. That'd be great.
There's been a lot of questions in here on the 2 HMCs. I'm not a subject matter expert in that area. Are you able to comment on that at all, Joe?
Just the fact of why there's the requirement for 2 HMCs, or what's the question?
Yeah, there's. First off, did you say 2 HMCs are required? Why does it need 2 HMCs? There's several people asking why is there 2 HMCs needed.
I'm not sure what happens if you only connect one HMC. I'm not sure. This is a chart that I found that said that they're required, but I think it's really for redundancy reasons. And like I said, the E1080 is really all about resiliency and having redundancy. Now the system will run without an HMC. You just can't do any management to it without an HMC. But I don't really know what would happen if you only had one connected. So that's something we'll have to find out.
And it doesn't have to be a physical HMC either, right? Don't forget, we can use an upgraded CR1 or CR2, plus there's the virtual HMC as an option.
Exactly, right. So back here in this chart, option 3 is you can use
you've
two
had
virtual
that there. Sorry, I
HMCs.
was answering questions. I didn't see that one.
Yep. So you have 3 options, either two appliances, appliance and a virtual, or 2 virtuals. Mostly what I see is people usually have at least one appliance, is what I've seen in the past. A lot of people do one appliance and one virtual, but like I said, they're fully, the virtual has all the functionality as the appliance. They're the same that way, so it really doesn't matter.
So
and
I'll try to
get
virtual
will run. You can buy the virtual HMC to run either on a power system under an LPAR of an existing power system, or you can buy the virtual HMC to run on x86 system that you have in a VM. If it's running on a power system, it can't manage the power system that it's running on. All right, and I always make the joke that my manager tells me that I can't manage myself, and that's why I need him. But virtual HMC can run on a power system, an existing one that you have, but it can't manage that system. So a little bit about operating systems. I had in that one chart all the operating systems, but this has a little bit more detail, so let's kind of just crawl through this chart a little bit here. AIX 7.1 is supported, TL5, SP5, but only with virtual I/O. Okay, so all the I/O has to be virtualized if you're running AIX 7.1. AIX 7.2 is supported, but only in P9 mode. And what does that really mean? It means that that code running in AIX, those applications running in AIX 7.2 won't really have access to the matrix math accelerators. All right, that's mostly what it means. I'm not sure, and I asked our AIX expert Carl Burnett on this, about this, and he said he doesn't really think that there would be much of a performance impact between the two. I mean, it's whether you're in P9 mode or P8 mode, they both support SMT8, but you would not; those applications would not have access to the matrix math accelerators. So AIX 7.3, gosh, not even announced yet, but we've talked about it. IBM has made a statement of direction, so I get to talk about it. And I'm even going to go so far as to say you're going to hear an announcement here pretty soon, like next month. And in the next VUG webinar that I do, we're going to have our AIX 7.3 experts on to tell you all about it. So AIX 7.3 imminent and supports full Power10. Right? IBMI, key thing, IBMI support is only in 7.3 and 7.4. You can't run IBMI 7.2. And certainly not 7.1 in the Power10 system, E1080. So, and know that for the IBMI customers. And then, of course, I won't go through these in detail, but we support RHEL, Linux, SUSE Linux, and OpenShift are all supported on the E1080. VIOS has to be 3.1.3, so new VIOS support for this. 3.1.3 improves on the scalability of performing multiple migrations. So if you're doing LPM, enhances the algorithm really to select the optimal mover service partition, the MSP, LAN adapter, and that balances the load for the LPM operations. PowerVM 3.1.3 also provides a new maintenance tool, which is for guided patching and support for the virtual I/O operating systems. So there's some benefits to VIOS 3.1.3, and this is what's required for Power10. One note here, back in the day, a lot of people, well, used to do, still do, same serial upgrades. So and these really were mostly for our higher end systems. So Power 7 Plus could go to Power 8, Power 8 go to Power 9, and you kept the same serial number all the way down here. And people did that for financial reasons. In order to do a same serial upgrade, a certain percentage of the system has to be moved to the new system. All right, it's a law. But Power 10, that's just not possible. The technology with Power 10 in too many places has changed, right? The processor's certainly changed. The OMI interface, all the memory and everything has changed. Too much of the stuff around it is all changed. And so Power 10 cannot do a same serial upgrade, all right? It's just, I'm sure for some people it will be unfortunate, but you just can't meet the legal requirements of doing that. So as you plan for Power 10, just know that that's not going to be possible. So that's really a lot of the system kind of stuff, but there's a lot of stuff around the Power 10 system that makes it what it is, where you want to run your mission critical workloads. And Power 10 is really built on these 4 pillars. And even Bill referred to a lot of this stuff when he talked just about the chip, because it's, most of these are all possible because of the chip. And this is persistent security, scalable, sustainable compute, top of the class reliability, and AI. And we're doing AI different, which Bill alluded to, and we're going to talk about that. So I'm going to kind of cover why in each of these 4 pillars, where we're at and what we're doing, and why Power 10, what's specific in Power 10 that makes this particular thing good, these pillars good. And we're going to start with security. So cyber resiliency, a little bit of a new term. It's kind of a combination of business continuity, which everybody's aware of, and cybersecurity, which is becoming a bigger deal every day. And kind of the combination of that, not just keeping your system up and keeping it secure, but what happens if you have a security breach. And actually Power 10 does a lot to prevent the security breach is what we're going to talk about here. But I just wanted to throw this up because the average cost of an hour of downtime in this study was $300,000 per hour. I know I think I've had some retail clients say it's more like $1 million a minute to them. But this is in this study it was $300K per hour. The average cost of a data breach, $3.9 million, or if you get a malware or a ransomware attack, $4.4 million. Pretty darn significant. And these are happening more every day. And so what's being done to prevent them is a big deal. And in Power 10, there's a lot of things that are in place to kind of help with this. You have to protect your data. You have to protect everything. You have to protect all your data. You have to protect your apps from being hacked and your system management, right? So you kind of have to look at the whole scale. You can't just look at data or just your apps. You kind of have to look at the whole thing here. And Power 10 is really designed to help in all 3 of these areas. One, by transparent encryption. We're going to talk a little bit about that. Out of the box there for every system. Cryptography engines that are being used, that can be used by the applications to protect the app from malicious intent. And integrated security management across the entire stack to help reduce the likelihood of administrative errors that might leave a hole for somebody to get in. So first of all, we're going to talk about encryption. Transparent memory encryption with every system out of the box, no additional management setup, built into the hardware, no performance impact. Bill mentioned the 4 crypto engines in every single core in Power 10. So this is one of those things you can look at and say, this isn't just an E1080 thing. This is going to be through the entire Power 10 product line, okay? Plus, Bill alluded to some of the current things, quantum safe cryptography, as quantum computers become more and more available out there, which is a way off, but they're going to be great crypto graphic code breakers there. We have to have a way to protect from that. Plus, fully homomorphic encryption, which is really a fancy word, a way of saying you can the ability to do computations on encrypted data without decrypting it first. And that's all just to make it faster, right? So those 2 things really in the bottom here aren't there today. That's not something that IBM is announcing or allowing, but they're built, they're available for future enhancements. And I think people, in particular this fully homomorphic encryption, something in the open source community can be working on and put into Power10 systems in the future. The management, we have Power SC, our Power Security and Compliance software that is sits on top of the Power Solution stack. It provides features such as compliant automation. We could do various industry standards, real-time file integration, integrity monitoring, the ability to report security audits, patch management, trusted logging, other things. Really need to do a whole session on Power SC. And again, this is something that if you want to see more on Power SC, when the webinar is over and you get the little survey up there, please put some comments in the survey and say that you'd like to see Power SC, and if so, then I'll do a session on that. We've covered it in the past. It was quite a while ago, so another session would be good. But a lot there to help with the management of your system to make sure that all your systems together are at the right level, and all the security stuff is in place. And if it's not, it sends you an alert. So let's look at the next pillar here, sustainable, scalable, and sustainable compute. We're going to look a little bit at the performance of the Power10. One of the key things in Power10 increases the per core performance over prior generations. Actually, every power generation has done that since the beginning. If you took this chart and you did it for Intel, it would be very flat or dip. Intel puts a lot more cores on their chip, but their per core performance does not generally increase generation to generation. And if you're buying software that's charged on a per core basis, then your software costs are going up significantly every generation. And I know Oracle does that, your OSs, your SWAMA, most of that stuff is all on a per core basis. So Power definitely gives you an advantage there. If we do some comparisons, first of all, let's look at an RPerf comparison here. Here's the different RPerf values for a Power10. This is the E980 and the E880, and just because generally people tend to jump a generation, I put the E80 performance here. And in the 10-core processor, it's 1.7x times per core performance improvement. In the 12-core processor, 1.8x improvement per core. So, and then of course the 880 doesn't have a 15-core option, so I couldn't put anything there. But you can see a pretty significant improvement here. If we look at, for the IBM I people out there who like to look at CPW instead, here's the same CPW numbers. They actually look a little bit better. In the 880, it's over 2x per core improvement from an 880 to an E1080. So pretty significant performance improvement there, which you can see here in this next chart, where you can take a Power10 2-KEK available today, 15-core system, and outperform the largest E880 system that we offered before by a little bit of a margin there even, right? So Power10 really does per core performance, not just the fact that we have only 3 cores more in there, but the per core performance is up, and actually did that. And Bill kind of showed, you know, the engines and the things that they've done by increasing cache, and all the things that they've done in the chip to increase that core. And it's pretty amazing. You know, we're not speeding up the clock speed anymore. Power 6 was our fastest clock speed. We ran around 5 gigahertz. Interestingly enough, everything's come down from there. And as you saw, it's all around the 4-ish gigahertz now. Power 8, or Power 7, Power 8, Power 9, Power 10, they haven't gone up there. They're all running around that same clock speed. So why are they faster? All the great stuff that our engineers are doing in the chip to increase the performance of the chip without doing it just by clock speed. Pretty amazing stuff.
Hey Joe, if I could just interrupt real quick. Something I actually forgot to mention, you know, and I'm a student of history, right? I worked on the Power 4 chip, and I hadn't done this in a while, but I went back and I compared the Power 10 to the Power 4 across the RPerf. and basically 112x improvement going from Power 4 to Power 10 at either the chip level or the largest system level, because they're both 16 sockets. So 112 times faster, better in terms of our perf score than Power 4 was 20 years ago. I just thought that was kind of an interesting amount of growth over that time.
Yeah, and only 20 years too. That is pretty amazing. Yep. So this has all been comparison of Power 10 to other power systems. But if we compare it to some Intel systems, this is a spec int, and of course there's a lot of different benchmarks out there. But integer operations are pretty popular, and I think this is pretty telling. Here's a HPE Superdome, still 8 sockets, a lot more cores, not quite twice as many cores, but over 100 more cores, so a lot more cores in here, and still a way better performance on this particular benchmark with the power system. In fact, 2.5 times more performance per core, right, and 1.3x more performance per socket even. So pretty significant compared performance improvement over Intel as well. And if we look at it a little bit different, so this is a spec in benchmark. Let's look at SAP. A lot of SAP customers out there. If you just do SAPs, and this is even more interesting because SAP isn't, you don't buy it on a charge by per core. All right, it's more by number of users. I think is the way they charge SAP. But you can see half the sockets, way less cores, and you still have more SAPs. And so what's the benefit here? Well, shoot, you have what, not quite a fourth, but better than that, less than that of number of cores. That's a lot fewer components to break, smaller systems, smaller footprints, better performance, less energy usage. So there's just all kinds of reasons why you would want to go with a power system using SAP than you would with either of these other two options. So just kind of wanted to show that it's not just compared to IBM, other power systems, that there's a performance improvement, but if you compare power to the other options out there besides IBM, it just looks good. And that's just performance. We'll look at other things as well. So besides performance, there's a lot of pressure now on companies to be environmentally responsible, and that's reduce their carbon footprint, which is the big term that's thrown around these days. And where do they look at when they get this kind of pressure? Well, one of the key things is they look at their data centers. Why? Because their data centers are chewing up a lot more electricity than anywhere else in their business. You have people in an office, they're maybe sitting in cubicles or offices, so they're kind of spread apart a little bit, and their lunch breaks and coffee breaks and all that kind of stuff. And then you have this room of computers that are all jammed together, happily eating their donuts in the way of electricity, right? And 10 to 50 times energy per floor space. And so that's why data centers are a key place. And if you can reduce your carbon footprint in your data center, it really helps your business out. And Power 10, with its increased performance, and not at the use of extra electricity, is one way of doing that. So just look at the Power 8. You get twice the performance of Power 8 with less than half the energy required. And so as businesses look to reduce their carbon footprint, power is one way they can do that. So let's look at the next pillar, and this one's going to be a pretty easy one because industry-leading reliability. And actually only have one chart on this because I attended a conference not last week, the week before, I guess. First conference customer meeting I've had since COVID. It was a kind of a smaller conference, but it was a great conference, and it was on Infor, so it's a application that runs on power systems. So it wasn't put on by IBM, put on by some business partners, and all the talk was about this application that happened to run on power systems. So it wasn't really on a power particular conference, but there's so many sessions I went to, and people were saying how good power systems run. They always run. They're great, and they weren't even talking about power itself. They were talking about their applications, but they liked the power platform. And this is why. It's because power is the most reliable system in the industry, right? Whether, well, okay, so we have System Z up here, and that's not power, but in the power platform, compare it to Intel, then it is the most reliable. So we'll sit behind our mainframe rhythm on that. And that's just been the case for years and years now. I don't think it's ever even disputed anymore. It's just the way it is. So, so I don't really have a whole lot more to say on that. And I want to move to the last column here and start wrapping this up with AI. And Bill talked about the AI a little bit and the matrix math accelerators on there. This is really putting it into the system and being able to do, as he said, inferencing where your data exists. Now in Power9 we had GPUs in one system, the AC922. It was great for training models, and you could do inferencing on it. It worked great, well. With Power10 we took another step forward and said we're going to put it in every system, MMAs in every core on a Power10 system, so you can do inferencing where your data resides. You don't have to move the data off somewhere, not transferring it anywhere, and you do it right there. And I think that is a key thing with Power10, a new benefit with Power10 as AI becomes more and more prevalent in the system. And just to kind of wrap this up, I talked about enterprise pools a little bit. You can run the 980 and the 1080 in the same pool. So previously you could only have the E980s in a pool. So now you can put 1080 in that same pool. If you have capacity credits, they can be used in that pool. So whatever capacity credits you've purchased for the Power9 will work on the Power10 system as well. All right. If you want to move, and I'm kind of getting towards the end here, so I'm just going to cover this chart here. If you want to move replace your Power9 with a Power10 in your pool, then you can do that. You can, when you transfer your base, you can move up to 3 Power E980 base activation features to the Power10. All right, for every Power10 feature. Okay, so let's say you have 40 on your Power9, and you want to move it to the Power10. You put you do a 3-to-1, so let's make it easy. 30 on the Power9, you buy 10 on the Power10, and those 30 could move over to the Power10, and then that Power9 could come out of your pool. All right, so you put the Power10 in, transfer your applications and everything, your workload over to the Power10. Your base processors move over to the Power10 as well, and then your Power9 can come out. All right. If you have mobile activations on Power9, there's a one-time ability to move those Power9 mobile activations to Power10. Now, all this on here is talking about Power9 and Power10. Power8 and Power10 cannot play in the same pool. All right. So if you have a mobile activation pool with Power8 and Power9, and you want to put a Power10 in there, you can't, because in a pool you can only have n and n+1. So you can't have Power8 and Power10 in the same pool. And there's no way to move Power8 mobile activations to Power10. If that's an issue, contact your IBM seller and talk to them about it. All right. And then I just want to, since we're kind of towards the end here, leave, I guess, maybe 1 minute for questions. Let me just open it up. Douglas, you've been kind of monitoring this, or Bill, if you guys want to have any parting questions or thoughts here.
The big topic there that sort of struck a chord was the HMCs. It's probably just recommended for needing 2 HMCs for redundancy. It's not a requirement. Someone did post a link about it in the Red Book, but we will have to go back and just validate and just double check that slide that mentioned required.
Okay.
So that was a big thing. There was also someone asked about Spectre Meltdown, and Bill, if you're still around, do you want to take a moment to comment on those mitigations?
Yeah, so Spectre Meltdown, I mean, that kind of arose, when we either had a bunch of hardware in the field, or we had, just kind of were on the verge of coming out with Power 9. So, we addressed those with, the right level of, firmware patches and various things, and basically, functionally covered the risks against Spectre meltdown. But because that was, kind of adapting existing hardware to address those, in some cases there were some performance losses. With Power 10, for the first time, we were able to address these proactively. We were able to go in the silicon and, kind of change the low-level silicon around to put, mechanisms that could address them, without incurring those kinds of, performance losses. So, just to be real clear, I mean, we're covered on it overall, but with Power 10, we're able to be covered on it in a more performant way. Does that make sense?
Absolutely. Okay, well, with that then, let me wrap up here and say, first, thank you, Bill. I know you're a busy guy. Thanks so much for taking the time to talk with the VUG community here. I really appreciate it. And thank you, Douglas, for being on there and helping out with questions. That was a huge, huge help. I really appreciate that.
No problem. And thank you to everybody for attending.
Yes.
Questions.
Yeah, thank you very much, and I enjoy the opportunity to take a little break from Power 11 to kind of talk about and celebrate Power 10. So thanks for the opportunity.
And so everybody, I've got the next bug, as I mentioned, set up. It's going to be on AIX 7.3. It's the October bug, but it's actually going to be in the first week of November. So don't be surprised with that, or don't be looking for the October thing. I'll send out an invite soon. But with TechU going on and everything like that, our subject matter experts wanted me to put it off till the first week of November. So we'll probably have two November ones.
On that, I mean, for folks who are interested in TechU and the Power 10, there are a whole bunch of Power 10 specific TechU sessions. So if you haven't already looked at the agenda and scheduling, please do take a look there. Any details I would have covered in a VUG session, I will be covering the exact same details in my TechU session. So good call on that one there, Joe.
All right. Thank you. Thanks, Doug. All right. Everybody, have a great fall and a great month.